Hello students, welcome to class 12 physics. In this video we are going to cover some of the numericals of chapter number 1, that is electric charges and fields. So today first of all let us solve illustration number 12. An electric field is uniform and in the positive x direction for positive x and uniform with the same magnitude but in the negative direction for negative x. That means here we are having the electric field along the x-axis, along the positive x-axis also, along the negative x-axis. It is given that E equals to 200 I Newton per coulomb for x greater than 0. That means for the positive x, the electric field value is 200 and you can see here it is denoted by I cap. Even if it is not given whether it is along the positive x-axis or negative x-axis, you can denote by this also. That is I cap that shows the positive x-axis direction. So magnitude is 200, direction is along positive x-axis. And E equals to minus 200 I cap Newton per coulomb for x less than 0. Here it is x less than 0. Here you can see that magnitude is 200. Here minus sign denotes the negative direction, opposite direction. That is minus I cap. That means this electric field is along the negative x-axis. A right circular cylinder of length 20 cm and radius 5 cm has its center at the origin. That means here you can see over here the figure. We are having a cylinder whose length is 20 cm and the radius is, here let us denote by R, its radius is 5 cm and it has its center at the origin. That means the center of the cylinder, it is placed at the origin. So from this origin, here it is the positive x-axis, from the origin to the left hand side it is negative x-axis, which is the line of the electric field. And its axis along the x-axis. That means here you can see from the origin to the x-axis, that is the center of the cylinder itself. So that one face is at x equals to 10 cm and other is at x equals to minus 10 cm. That means from this origin to the one face of this cylinder, that is at 10 cm plus 10 cm because it is the positive direction. From origin to the other face of the cylinder, that is minus 10 cm. That means it is 10 cm away from the origin but in the negative direction. So it is minus 10 cm as shown in the figure. What is the net outward flux through each flat face? Here we are going to find the flux. So from this figure you can see the x-axis is shown for the electric field. Center of the cylinder, it is at origin and here it is y-axis. Length of the cylinder is 20 cm, radius of the cylinder is 5 cm. We need to find the total flux. That means first we will be finding the flux at this end, then we will be finding the flux at this end, then we will be finding the flux at this surface. So first of all let us convert this, let us write the data. E for x greater than 0, that is 200 I cap Newton per coulomb. Then we are having the data for x less than 0, it is E equals to minus 200 I cap Newton per coulomb. Then here we are having the distance from origin to this and here we are having the second end, so let us write x2 equals to 10 cm. Converting that into meter, that will be 0.1 meter. In the same way this end, from origin to this face, let us denote it by x1. It is minus 10 cm, that is minus 0.1 meter. This minus just shows the direction. Now we are having length as 20 cm. Let us convert that into meter. That is 0.2 meter. As well as data from the given statement. Now let us find the flux at the end 1. Flux through phase 1 of the cylinder. We know the general formula for the flux, that is, we are finding for phase 1, so let us denote by phi 1 equals to E1 A1 cos theta. Here theta is angle between the E1 vector and A1 vector. As you can see over here, the electric field is along negative x-axis and the area vector is always normal to the surface. So the surface is like this and the area vector will be normal to that. So you can see the electric field and the area vector both are parallel to each other. Here E1 vector is parallel to A1 vector, therefore theta equals to 0 degree. Thus phi 1 equals to E1 A1 because cos 0 that is 1. Now electric field that is given here for x greater than 0, let us denote by E1, that is 200I, and area vector, here area vector we are given just a radius, and for these phase, right, for these circular phase, the area will be pi r square. So here it is E1, area is pi r square. E1 that is what? That is 200 and pi r square, pi that is 3.14 into radius that is 0.05 square. Here the value of this pi r square, that is 3.14 into 0.05 whole square, that is equals to 7.85 into 10 raised to minus 3. Thus the flux, when we calculate that, calculating this, we get 1.57, that is Newton per coulomb into meter square. So flux of the phase 1 of the cylinder, that is 1.57 Newton per coulomb into meter square. Now in the same way we will be finding the flux at the end 2, that is of the phase 2. Here let us say phi 1 is this much value, phi 2, that is flux through phase 2 of the cylinder. The same way you can see from the figure, electric field, right, that is along the positive x-axis. Area vector, again the phase is like this, area vector is normal to the phase. So electric field and this area vector both are along the same direction. We can say they are parallel to each other. First of all, let us write the general formula. Flux, that is Ea cos theta. Here we are denoting phi 2 for phase 2, E2 A2 cos theta. Again here E2 vector is parallel to A2 vector, so theta is equals to 0 degree. Cos 0 that will be 1. So let us write phi 2 equals to E2 A2. Again for these phase also, the surface area of this phase of the cylinder, that is the circular phase, we can write again area as pi r square, right? Electric field along this direction, that is plus 200 phase 2. Now, here for this curved surface, you can see the electric field is along this direction. If I take this area vector for this curved surface, for this surface area vector will be normal to that. So, electric field in this direction, area vector in the above direction. The angle between that is 90 degree. And for that, when we apply the formula for curved surface, phi equals to EA cos theta. Let us denote it by 3. Here, E3 vector is perpendicular to A3 vector and cos 90 degree. That is theta equals to 90 degree. Cos 90 degree, that will be 0. So, flux through that will be 0. So, flux for this curved surface, that will be 0. Now, here we need to find the total flux. So, total flux, that will be what? Phi equals to phi 1 plus phi 2 plus phi 3. Phi 1, that is 1.57 plus 1.57 plus 0, that is 3.14 Newton per meter square. So this is the net outward flux for the cylinder. So students, you may copy down this. Now let us solve the textual exercise numerical number 15. So first part is, consider a uniform electric field E equals to 3 into 10 raised to 3 I cap Newton per coulomb. What is the flux of this field through a square of 10 cm on a side whose plane is parallel to YZ plane? So what is given over here in the first statement? Consider a uniform electric field whose magnitude is 3 into 10 raised to 3. Unit vector I shows that it is along the x-axis. So let us draw this figure first. Along the x-axis is electric field and its magnitude is 3 into 10 raised to 3 Newton per coulomb. Then what is the flux of this field? We need to find the flux over here of this field through a square of 10 cm on a side whose plane is parallel to YZ plane. That means we are considering a plane which is in the form of a square and its side is given as, that is 10 cm, that is 0.1 meter. Along YZ plane, where is the plane? It is along the YZ plane. So let us consider that this as the y-axis, this as the z-axis, and d square it is on this YZ plane. The square is along the YZ plane and its side is 10 cm. Okay. We need to find the flux over here. You can see over here the electric field is along the x-axis and the square is in the YZ plane. The area vector of this, because it is in the YZ plane, the area vector which is normal to the YZ plane, that will also be along the x-axis. That is the area vector normal to this YZ plane Here theta is what? That is angle between the electric field vector and the area vector. So here, as you can see in the figure, E and A are parallel to each other. Therefore, theta equals to 0 degree. Theta equals to 0 degree, that is cos 0, which is 1. So, flux equals to EA. You can see over here, the magnitude is given 3 into 10 is to 3. Area, that is what? That is the area of this square. So, that is nothing but area is of the square, that is length into length, that is L square. E is 3 into 10 is to 3. Length over here is 0.1 meter. So 0.1 square, which is the area of the square. When you calculate this, we get the value as 30. Because it is flux, its unit is Newton per coulomb meter square. So this is the flux through this plane square surface whose area vector is along the x-axis. Now let us see the second part. What is the flux through the same square? If the normal to its plane makes a 60-degree angle with the x-axis. What is given? We are taking the same square whose length is 10 centimeter. But now the area vector, the same square, if the normal of its plane, that means the area vector of the square, it is making 60-degree angle with the x-axis. So the same scenario, x-axis is having the electric field direction, but the normal to the square, that is the area vector of the square, because we know that the area vector is always normal to the any surface. So here it makes the area vector of the square. So let us consider this plane or the square, right? Normal to the square is the area vector, and that makes an angle theta, which is equals to 60 degree with this electric field. Now, applying the same formula, we are going to find the flux over here, but scenario is different. EA cos theta. Here theta is given, that is 60 degree, so EA cos 60 degree. Electric field value, that is same, 3 into 10 raised to 3. Area, that is area of square, we are taking the same square of 10 centimeter, so 0.1 square, L into 12. Cos 60 degree, that is half. So when you calculate this, we get the value as 50 Newton meter square per coulomb. So this is the flux of the square, flux passing through the square, when its area vector makes an angle 60 degree with the electric field. So students, you may copy down this.